Minimum phase and all-pass systems occur naturally in the study of difference equation descriptions for systems using the Z-transform. We know from our analysis of inverse systems that a stable causal system has a stable causal inverse if and only if all the poles and zeros of the system lie inside the unit circle. Well, this is what we call a minimum phase system. It's a system that has all its poles and zeros inside the unit circle. And it turns out that you can show that the phase lag of a system with its poles and zeros inside the unit circle is less than that of any other system that has identical magnitude response. That can be shown using all-pass systems, which we'll look at in a moment. It turns out that we can write any rational system function h of z that doesn't have zeros on the unit circle as a product of a minimum phase system, h min of z, and an all-pass system, h all-pass of z. And this decomposition will be useful when we consider trying to find approximate inverse systems for h of z. But first let's look at all-pass systems. What it means for a system to be all-pass is that the magnitude of its frequency response is equal to 1 for all frequencies. So it treats all frequencies identically with respect to gain. The general form of an all-pass system is to have the poles and zeros occur in conjugate reciprocal pairs. So an arbitrary all-pass system can be written here as a product, I equals 1 to p, of pole zero pairs, where my pole here is at c sub I, and then my zero ends up being at 1 over c sub I complex conjugate. If I have a pole at c sub I and I write that in polar notation so that the pole has magnitude r and phase angle phi, as I've drawn on this picture of the z-plane, then when I look at where the zero would need to be located to be in a conjugate reciprocal pair, it turns out that I end up inverting the magnitude of the pole, but the angle stays the same because conjugate's going to change j to minus j, but that's in the denominator, so the phase ends up being back at phi. So I have a pole at r e to the j phi, then my conjugate reciprocal zero is going to be at 1 over r e to the j phi. Since each of these terms will have unit gain at all frequencies, as we'll show in a moment, so I can multiply as many of those as I want together to get a general pth order all-pass system. Now to look at the magnitude response of an all-pass system, we're going to just consider one term, because if we can show that the magnitude response is 1 at all frequencies for a single term, then when I multiply all those terms together, it'll also be 1. So let's take the case where we have a pole at c and a zero at 1 over c conjugate. So I'm going to replace z. Remember, I had z inverse minus c complex conjugate divided by 1 minus c z inverse. We're going to replace z inverse by e to the minus j omega. In other words, evaluate the z-transform on the unit circle to get the frequency response, and we'll take the magnitude of that. So I can write that as e to the minus j omega minus c conjugate over 1 minus c e to the minus j omega. Now in the numerator, I'm going to factor out the e to the minus j omega term, so I can write the numerator as e to the minus j omega times the quantity 1 minus c complex conjugate e to the plus j omega. Next, we'll recognize that we have a product here, and so the magnitude of a product is the product of the magnitudes, and this particular term, the e to the minus j omega term, is going to have magnitude of 1. So I can factor that out, and I'll write what's left as 1 minus e to the minus c complex conjugate e to the j omega over 1 minus c e to the minus j omega. Now at this point, a bit of inspection reveals our desired result. Let's call the denominator here b. Well, if we compare the denominator and the numerator, we see that the numerator is just the complex conjugate of b. So what I have here in the denominator, I've got the magnitude of b, and in the numerator, I've got the magnitude of b complex conjugate. Well, the magnitude of the complex conjugate is identical to the magnitude of the number, so that leaves this ratio being exactly 1. So an all-pass system that has terms of the form z inverse minus c complex conjugate over 1 minus c z inverse is going to have unit magnitude when we evaluate this on the unit circle. It passes all frequencies equally. We've got an example here where we took a pole at 0.9 in one case, the case on the left, and then in the case on the right, we put the pole at minus 0.9. And you can see that if I evaluate a system of this form, so this is going to be, let's take the case where c is 0.9. I'll have z inverse minus 0.9 divided by 1 minus 0.9 z inverse. And that has magnitude response of 1 for all frequency, and the phase response is fairly steep initially and then flattens out and ends up at minus 180 degrees. If I move the pole to the other side of the real axis, to the negative real axis, over here at minus 0.9, then it turns out the phase response is relatively flat initially, and as we get close to frequency pi, it gets much steeper. Okay, so those are two all-pass systems. You can see that it has, both of them have the same magnitude, which is unity for all frequency, and they just have different phase responses depending on where you put the pole. Now, one of the useful things we can do with an all-pass system is write an arbitrary system as the product of a minimum phase term and an all-pass term. And again, this decomposition requires that h of z does not have any zeros on the unit circle. So what we're going to do is take all the zeros of h of z that lie outside the magnitude of z equals 1 and move them into the all-pass term. And then we will add poles to the all-pass term at the conjugate reciprocal locations of the zeros that we move into the all-pass term. So at this point, we have poles and zeros here in h all-pass that are in conjugate reciprocal pairs. Now, to keep the right-hand side of the expression the same for this product, we've added poles to h all-pass. We need to add zeros to h min in order to cancel those poles and retain the equality. So we're going to put these zeros then in h min. And what we've done, because the poles that we added to h all-pass are all inside the unit circle, the zeros that we add to h min are also inside the unit circle, and in effect we've reflected the zeros that were outside the unit circle back inside the unit circle for the minimum phase component. Now let's do a little example. Suppose that we have one zero that is located outside the unit circle in h of z. So I've written that zero here as 1 minus beta z inverse, and we're assuming the magnitude of beta is greater than 1. And then that h1 of z has all its zeros and poles inside the circle. So h1 would be a minimum phase system. Well, we want to write h of z as a product of a minimum phase system and an all-pass system. And it's not quite in that form yet because this is not an all-pass system. So to make that an all-pass system, we're going to first factor that zero out and put it in the form of the zero for an all-pass system. So remember, the all-pass system has z inverse minus 1 over the zero location. So to get that form, I'm going to factor out minus beta. If you forget to factor out minus beta and you write this as 1 minus beta z inverse over 1 minus 1 over beta conjugate z inverse, you won't have unit gain. You'll have a gain given by beta. So we need to factor this out. Now we've put the zero into h all-pass for the first step. And so to do the second and third steps, we need to put a pole into the all-pass term that's at the conjugate reciprocal location of the zero, and that's obtained by putting a pole at 1 over beta complex conjugate. And when we introduce this pole, to keep this equality on the right-hand side, we have to also introduce a zero at 1 over beta complex conjugate. This zero, of course, is inside of the unit circle, whereas my original zero was outside of the unit circle. So now we have our decomposition. This first part here is h min of z, as I've indicated in the magenta color, and then the second term is in the form of an all-pass filter. So in a sense, what we've done, starting up here with h of z is we've taken the zero that was at z equals beta and obtained a minimum phase system by reflecting that zero back inside of the unit circle. Since the all-pass component has unit magnitude response at all frequency, this operation of moving a zero from outside the unit circle back inside the unit circle as a conjugate reciprocal, turns out it does not change the magnitude response. So the magnitude response of h min is the same as that of h. Of course, the phase response is different, and that's because the all-pass system is going to contribute some extra phase beyond the minimum phase associated with h min. Now, one value for this decomposition is that we can always equalize or invert the minimum phase component of h. And we can do this as follows. So if I decompose h into a minimum phase component and an all-pass component, then I can take the output of that system and run it through the inverse system for the minimum phase component, because this has all its poles and zeros inside the circle, so I can get a stable causal inverse system. And then the net effect is as if I passed my original signal through this all-pass system. So I don't have any magnitude distortion. In other words, the original signal has a certain magnitude at each frequency, and that's not changed by this process, but we do get some phase distortion. And depending on the application, that phase distortion may or may not be important. For example, the human auditory system is not very sensitive to phase distortion. I've got an example here where I have 4 zeros. I have an all-zero system, and then there's 4 poles to match that up at the origin at z equals 0. So in this system, we have 2 zeros that are outside the unit circle. They're located at plus or minus 1 over 0.9. So it's this 0 here and this 0 here. And then we have 2 poles that are located on the imaginary axis at plus or minus j times 0.7. Well, if I look at the magnitude response of this system, I see that it varies in its gain from 0.25 or 0.3 almost to 1.5. And then down again and back. And the phase response kind of wanders around in a nonlinear fashion. Well, I can take these 2 zeros that are outside the unit circle and absorb those into an all-pass component and then replace them by zeros that are reflected inside the unit circle. My all-pass component is going to be z inverse minus 0.9 and z inverse plus 0.9, and then I'll have 1 minus 0.9 z inverse, 1 plus 0.9 z inverse. So I've moved these zeros back inside the unit circle for h min, and then what I have for h all pass, we'll end up putting a pole here and here that pairs with this zero that was outside the unit circle. So my minimum phase component can be written as I've shown here in the green, and you'll note that I've reflected the zeros inside the unit circle. So we have a 1 0 at 0.9, another 0 at minus 0.9, and then there's a scale factor of minus 0.81 that comes out when we rewrite the all-pass component as z inverse minus 0.9z. So I've displayed here the magnitude of the all-pass component and the phase response. So if I were to equalize the minimum phase portion of this original system, h of z here, what I'd be left with for the response of the equalized system would be this all-pass term, which consists of no magnitude distortion, and then this phase characteristic here that's associated with the all-pass response.